So in this lecture, what we are going to look at are different applications. So far what we have seen are different types of processes, and in the second part of the lecture we have seen the different mechanisms, pore flow mechanism or diffusion through the membrane or solution diffusion model. Here we are going to see now how do we apply all these things to different membrane separation processes. The first we are going to see is microfiltration, ultrafiltration and nanofiltration. The reason being they are very similar, they only differ in the size of solute that is getting filtered. So first of all, what we would like to do is to write an expression or get an expression for what kind of solutes, what kind of sizes of solutes are filtered by a different membranes. So imagine that there is a membrane, we are looking at cross section of the membrane, let's say top view of the membrane. Imagine that this is one pore of the membrane. So let's say pore size is capital R. There is a solute of, let's say it's circular or it's a spherical, or let's say in the cross section it will appear as a circular. So it's a solute having radius A. Now the solvent that is there, the size of the solvent is very small as compared to the size of solute. So the solvent area available for this solvent is this whole cross sectional area, whereas area available for the solute to flow is only this inner cross section area. So what we are going to write first is what is the volumetric flow rate of solvent that will go through here, this whole area, and what is the volumetric flow rate of solvent that will go through this inner area. Okay, then that ratio, obviously the amount of solvent that will go through this inner area is going to be smaller than this bigger area. That ratio is called as steric ratio because part of this area is not available for the solute to go through. So if you multiply the flow rates by the concentration, you will get how much flow rate is there of the, or what is the rate of transport of the solute going through this area, divided by what is the total maximum possible rate at which solvent will go through. Or if the whole solvent, if the solute was very small in size, it will allow the whole solute could be transported through this whole area. So that ratio we are going to call as what is the rejection of the solute. Let's just come to this in a minute. Okay, so here is what we are going to do. We are going to define steric ratio as the volumetric flow rate that will go through the inner circle having radius r minus a, divided by the total flow rate that will go through this whole pore of radius r. So if the flow is laminar, the velocity Vz is related to the average velocity and 1 minus r by r the whole square. Now at this point you should substitute this Vz here and do the integration numerator and denominator and get an expression for steric ratio yourself. So pause this video, do the integration and calculate steric ratio. Okay, so what you will find is the steric ratio is given by this expression. So what this means is that if I allow solute only to go through this area versus I allow solute to go through this whole area, that is like how much solute is rejected from the membrane. So percent rejection would be 1 minus this steric ratio into 100. So I will get an expression for percent rejection of the solute. This equation is called as Perry-Renkin equation. It is very useful because it allows us to estimate what is the rejection of a solute of radius a as compared to the pore of going through a membrane having pore of radius r. So you can very clearly see that if the solute size is equal to the radius of the pore, that means solute radius is equal to the radius of the pore, we will have 100% rejection of the solute. No solute will go from the feed side to the membrane side. Whereas if the solute is very small in size as compared to the radius of the pore, rejection will be practically zero because this number will be practically zero. So it will have 1 minus 1. You will have 1 minus 2 times 1 plus 1, you will have rejection practically being 0. Now we can replace this A by molecular weight of solute and this R as the molecular weight at which 100% rejection will happen. That means if the molecule is of a size equal to R, it will be completely rejected by the membrane. We can convert that into the molecular weight that we call as molecular weight cutoff. Here is what I mean. We can define another term as called as solute sieving coefficient. Sieving coefficient would be the concentration in the permeate side divided by the feed side. So obviously you can see that the rejection and sieving coefficient, they are related to one another. So especially when we are talking about water, very commonly we want 99.99% of the solutes to be rejected. Say for example, if we are talking about removal of bacteria from water, we require 99.9999% rejection of bacteria. If we are talking about viruses, very important these days, we require 99.999% rejection. These are all WHO guidelines. If we are talking about cysts, we require 99.99 reduction in terms of the cyst based on the permeate and the feed side. So sometimes we don't like to say so many nines. We talk in terms of log to the base 10. So if I have 99% rejection, then this number would be 0.99 and log to the base 10 would become log 2. So we can think in terms of if you think that if you think in terms of 99.99% reduction, just a small correction, then this CIP, just a small correction, this is actually CIP divided by CIF, right? So let's continue. So if we talk about 99.99% reduction or 99% reduction, then this CIP would be 0.01 and log to the base 10 would become 2. So that's 2 log reduction. So 2 log reduction would mean 99%. If we have 99.99% reduction, this CIP divided by CIF would be 0.0001 and minus log to the base 10 would become 4 log reduction. So 4 log reduction would mean 99.99% removal. So you can see the rejection coefficient and the sieving coefficient, they are related. Now going back, we can write the rejection in terms of the molecular weight of the solute. We replace this A in terms of the molecular weight of the solute and replace R in terms of what is the maximum size of the solute. That we give 100% rejection. So the maximum size would be related to capital R and we call that particular molecular weight as molecular weight cutoff. So we are going to replace this A by molecular weight of solute and R by molecular weight cutoff, which is the molecular weight which will have 100% rejection. Okay, so if we do that for yourself right now. Pause the video, do the calculation, then only go forward. So if you do that, you will find that rejection will be 1 minus 2 times 1 minus molecular weight divided by molecular weight cutoff raised to 1 by 3 the whole square. We are of course neglecting the second term, this term, because this term is small, very small as compared to this term. It is raised to 4, whereas this is only raised to power 2. Okay, so what different molecules we can take for characterization of the membrane in terms of molecular weight cutoff. So what we will do an experiment is we will take different molecules on the feed side, measure the feed side concentration, allow filtration to happen, measure the permeate side concentration, then based on the concentration in the permeate side divided by concentration in the feed side, we can calculate the rejection of that particular membrane. Now if I take different solutes and do an experiment with respect to a particular membrane, we will find that for some particular size the rejection would be 100% and then that would be called as molecular weight cutoff. So for example, if I take sucrose, molecular diameter would be 11 angstrom, that is 1.1 nanometer. Molecular weight would be 340. If I take, let's say, insulin, molecular weight would be something like 5700. The molecular diameter would be something like 27 angstroms, 2.7 nanometer. Now, if I take a particular membrane and pass these solutes through the membrane, or try to pass these solutes through the membrane, small molecules will directly go through. They will have 0% rejection, whereas big molecules will have 100% rejection. They will not be able to go through. And the size at which we will get 100% rejection, we will call that as molecular weight cutoff. Let me just explain. Let's just look at one such membrane. Each line here represents a membrane with a different molecular weight cutoff. So if I take this particular membrane and try to pass different solutes, so if I pass insulin, for example, through this membrane, it will be maybe having, let's say, about 40% rejection. But if I try to pass higher and higher molecular weight compounds, meaning higher and higher sizes, they would have, for this particular membrane, higher and higher rejection. So a molecular weight which gives almost 100% rejection, we call as the molecular weight cutoff for this particular membrane. If I take another membrane, this membrane has a different molecular weight cutoff. Okay, so you can see that different membranes have different molecular weight cutoff, and we can calculate, measure experimentally the molecular weight cutoff of the membranes by trying to permeate or trying to pass different solutes through this membrane. We can of course calculate all this. So for example, if I take a particular solute size and I take different membranes with different pore radii. So for example, a membrane with 25 angstrom pore radius, 2.5 nanometer pore radius, or a membrane with 5 nanometer pore radius, 50 angstrom pore radius, or a membrane with 100 angstrom pore radius, 10 nanometer membrane. So if I have a particular size of a membrane, a particular size of the solute, if I take smaller and smaller membranes, it will be rejected to a larger and larger extent. So for example, if I pass this particular solute through a 100 angstrom cutoff, 100 angstrom pore radius membrane, it will have a very small rejection because the membrane size is big. It is allowing entire solute or majority of the solute to go through. So using this as well, we can characterize what is the molecular weight cutoff for different sizes of membranes. So sometimes this molecular weight cutoff can be very, very sharp. So you see this particular membrane versus this particular membrane. So this particular membrane of course has a molecular weight cutoff larger than this particular membrane, but it is also, this one is very sharp. The rejection versus the molecular weight, the curve is very sharp, whereas this one, the curve is very gradual. So this is called as a diffuse cutoff membrane. This is called as a sharp cutoff membrane. Obviously, if the size of the pores are all same and all uniform, you would have a very sharp cutoff. Whereas the membrane is made with a large pore size distribution, you will have a diffuse cutoff. Also, if the membrane has some pinholes, defects, it will have a very diffuse cutoff. So for applications, what we want, wherever we have two molecules which are having small difference in size, we would want a membrane to be of a sharp cutoff. So you see, if molecular weight is between 1000 and 10,000, 1000 molecular weight will have zero rejection, whereas a 10,000 molecular weight will have a practically 100% rejection. But here, for this particular membrane, even a 1000 molecular weight cutoff has some rejection, whereas even a 100,000 molecular weight has a doesn't have even 100% rejection. 10,000 would have a 50% rejection. That's because this is called as a diffuse cutoff. You will not get a good separation between solutes in this particular membranes, whereas the selectivity or the kind of separation that we will get would be very nice if it's a sharp cutoff, very large if it's a sharp cutoff membrane. Okay, here is what I want you to think about now. What I want you to think about is, let's say I want to filter out a particular solute, okay, and I apply a given pressure difference, and we take membranes with different pore sizes. I would like you to qualitatively plot how the rejection and flux will vary across membranes of different pore sizes for a given solute. Okay? Pause this video, plot this qualitatively before going forward. Okay, here is something that you will see. If I take membranes of different pore sizes, if I increase the pore size for the same solute, the rejection will reduce. Okay, that's coming from this equation. If I take same molecular weight, make same molecular size and different pore sizes, as the pore size goes up, rejection will go down. Or from here, if I take a molecule of a particular molecular weight and I take different molecular weight cutoff membranes, higher and higher molecular weight cutoff membranes, pore size increasing means higher and higher molecular weight cutoff membranes. So what we are looking at is either in terms of pore size or different membranes having different molecular weight cutoff. If you are increasing the molecular weight cutoff, then the rejection would fall. It will allow molecules to go through. But the flux will increase because now the resistance of the membrane. Remember about our relationship about permeance of the membrane related to the square of the diameter of the pores. So the flux would increase as we increase the pore size, but rejection would fall. So now this is a trade-off that we have to do. We have to design a membrane at which we will get a particular desired kind of rejection. Let's say I want, let's say 99% or 95% rejection. I will choose a membrane that will automatically fix, or it will limit my flux to this value. Whereas if I take a 90% or a 80% rejection, right, it will allow me to have a higher flux to the membrane. Okay, and of course, if the membrane is made of pores which are having extremely narrow pore size distribution, then I can get a very nice rejection and at the same time get a very high level of flux, because it will allow only the solvent to go through. It will allow membrane to reject the particular solute. If the membrane is having a large pore size distribution or a diffuse molecular weight cutoff, then this selectivity or rejection versus flux trade-off becomes very, very important. Just some typical values for you to remember, or for you to work with. If you have a microfiltration membrane, typical transmembrane pressure you will keep between, let's say, 1 to 5 bar. If you have ultrafiltration membrane, pore size is becoming smaller and smaller, so we need to increase the transmembrane pressure. If I look at nanofiltration, pore size is becoming even smaller, we need to increase the transmembrane pressure to higher and higher values, 20-25 bar, and correspondingly the flux through the membranes will drop. Okay, just these are some guidelines, just some values which are experimentally observed in reality. So what we will do now is we will try to apply all this what we have seen to different kinds of microfiltration or ultrafiltration membranes. We will see that in the next part of the lecture.